So welcome everybody to this new seminar. So we have the pleasure to have today Nicolas Stoll as a speaker for our fortnightly seminar. And Nicolas is a PhD student from the Alfred Wegener Institute in Germany, and is working on Raman spectroscopy analysis of ice core. And today he will talk about microinclusion and deformation in the EGRIP ice core. So please, Nicolas, the floor is yours.
Okay, perfect. Yeah, thanks for having me. I'm happy to give this little talk today. It's not just me, there are a lot of people involved in this entire project and also in the data I will present. So some of them are listed down below. It's a very international team, also some from Italy, and I'm very happy to add some more. So I would like to thank Pascal and Carlo and Marco and Alessandro already for the last couple of weeks. I've been here in Venice and doing measurements, but I will get to this in the end. So first of all, I would like to tell you something about the EGRIP ice core and what I've been working on over the last years, and then we come back to what I've been doing here in Venice. Okay, so first of all, I would like to have you all to take a look at those images. I think you're all aware and you know about cloudy bands in ice. And I think here it is shown very nicely that impurities in microstructure in ice, they go hand in hand. So from the meso large scale on the left to the zoomed in scale in the middle to the very detailed view on the right, you can see those little dust inclusions here in the ice. And especially if you zoom in and look on the right hand side, you can see how you can locate them in the microstructure. And what I've been trying to do over the last years is trying to get those two things together. And I'll talk about this today. So first of all, microstructure, maybe not all of you are too familiar with it, but it's basically the shape and the size of ice grains and also their crystal orientation. And on this little animation here, you can see ice flowing to the right, being sheared, and the crystal orientation changes here also, and also the grain shape and the grain sizes. And this is just a little thing to show you that when you look at flow of ice, for example, in glaciers, but also in ice sheets, and especially in ice streams, you have to look into the details, into the microstructure to get the large scale deformation right, which is then important to get the flow of ice right in the end. Since it's not just sliding, there's also a lot of internal deformation going on in the ice. And this is what the working group I'm part of is working on mostly. So the small scale deformation of polar ice. And how do impurities take part in this? Just one example. Just imagine these are ice crystals on the left, and now they are being deformed, and you can see how the 3D shape and the volume changes. I hope that's okay via the screen, the stream, but you should be able to see how those crystals change in all dimensions. And this can be impacted by impurities, and there are two main processes which are known from metals, for example, the drag of grain boundaries. So when you have impurities, they somehow get dragged along the grain boundary, and the grain growth is declining, is somehow restricted. And similar pattern happens when you have Zener pinning. So the grain boundaries, they don't move at all anymore. They are somehow pinned. If you have a so-called large impurity, then they hardly move at all. And those are two example processes where impurities and microstructure are acting together. And we are still trying to figure out how this is exactly happening and what is actually happening. When I study those, here I just compiled a very long table of studies regarding impurities and also microstructure over the last 2 decades. Please don't try to read all of them. This is just to give you a small impression of what has been done and what methods have been used. So a lot of different methods, from classical optical microscopy to electron microscopy to Raman spectroscopy, X-ray spectroscopy, and also laser ablation, ICP-MS. And just to somehow summarize those results, they are quite ambiguous. So depending on the method, you find different results. And so far, there hasn't been a really systematic study where you can really compare your results, since it's such a high resolution field. You always just get very small samples, and it's really, really hard to generalize these patterns you can see here for entire ice cores or even the ice sheet. So what about EGRIP now? How can EGRIP, this new ice core, maybe help us? And the thing about EGRIP is, maybe you haven't heard about it yet, so I'll give you a very brief introduction. EGRIP is located in the northeast of Greenland. You can see Greenland here on the left and the flow lines where the ice is flowing, and you can see the northeast Greenland ice stream up on the upper right. So I'll just show it again. This is where most of the mass, which is counting for the solid ice discharge in Greenland, is being transported. And there we are drilling this EGRIP ice core. And this is this nice logo. And it's the very first deep ice core, which is being drilled to really get behind the deformation of ice. Not so much about the climate reconstruction, but about the deformation. And there are several challenges for that, but also a lot of stuff to learn from this new ice core. And even though it is still being drilled, we already have a lot of high resolution CFA data, IC data, and of course, a lot of physical properties data. So this includes the crystal orientation, grain shape, grain size data, but also dielectric properties, visual stratigraphy, and a lot more. And now we can add laser ablation data to this. So this is very new, still preliminary, but yeah, we did a pretty good job on this already, I think. Just to give you a brief introduction again, this is your basic glaciology 101, how to get to this microstructure data. You are in the field, you sample the ice core every 5 to 10 meters. You make thin sections out of the ice, you polish them at -20 degrees, and then you have those thin sections you can analyze. And here you can see the grains, and each color represents a different orientation of the ice crystal or the grain. You probably have all heard this somewhere in your career early on, but this is basically the microstructure part here. And out of this, we've got a lot of information already. So this is a sketch of the ice stream of the EGRIP ice core. We are currently down to 2,120 meters. And we can see already that we have this classical vertical compression in the upper part of the core. And then we really have some extensional deformation going on due to the ice stream. And this is already pretty cool because this was modeled and expected, but now we have the very first measurements and observational results, and they are hopefully published soon. We are still working on that. It gets a bit more difficult when you look into the details, but I will skip this today. And yeah, we had to stop in August 2019 at 2,120 meters, and then COVID happened. So last year we couldn't go back to Greenland, and this year we also can't go back, but hopefully next year. And we hope to reach bedrock next year. So there are another 500 meters to be drilled. And of course, the most interesting part of the ice core where the most deformation is going on. Okay, so how do we get to the impurities and to Raman spectroscopy now? So back at RV, we took our samples, which we have been analyzing on the physical properties already, and did microstructure mapping. So on the left, you can see one of our little ice labs in Bremerhaven in northern Germany at -20, and we did microstructure mapping. So you polish a surface or a sample, and you map the surface of the sample, and then you focus into the sample 500 micrometers below the surface and take another mapping here. And then you can go into this map and look for solid inclusions or micro inclusions. This is what I indicated here with those yellow dots. This is in the sample, so we avoid contamination. And then you use cryo-Raman spectroscopy, also in the cold lab. Put your little sample, so they are very small, normally 1 × 1 centimeters in length and width, and we analyze them. And this is what it looks like when you look through your Raman microscope. So those are those little inclusions we're looking for. They are really just a couple of micrometers, normally even smaller than that. And then you get a signal or a Raman, your Raman measurements. So Raman measurements, basically you shoot with a laser at your inclusions and the molecule starts to vibrate and you get a little bit of Raman scattering. There's a lot of different scattering and a tiny bit is Raman scattering, which allows you to get information about the molecule structure and therefore the chemistry, so the chemical composition of your molecule or your mineral. And this, for example, is gypsum, so you can identify those peaks. The very large peak on the left is always from your laser, your initial shooting at the inclusion. You have small ice peaks at 217 and the big one at 3145. And then the peaks in between you have to calibrate and then you have to identify them. And this example peak here is gypsum, so calcium sulfate. Okay, here again, just the overview about one of the samples. So this is what it looks like inside your sample, roughly 500 micrometers below the surface. You still see some traces of the grain boundaries and some air bubbles, some clathrates. And when you zoom in, those very tiny little dots, they are the inclusions we are looking for. Okay, and now I get into the data and the results. So we already made 2 manuscripts out of that, and they are under review at the cryosphere at the moment. So if you're interested in more details, just take a look at those 2. And what we did is we took 11 samples from the upper 1340 meters, which is all the Holocene, the Younger Dryas, and the majority of the building aerosols. So we are very young, so to say, but we have a very high spatial resolution when you're looking at impurity measurements, because normally there are just a couple of samples throughout one core, and we try to really have a good resolution here and to have samples roughly every 100 meters. And you can see the grain area here on the left in pink, and the dust particle concentration in green on the right, and then the detailed dust particle measurements and data on the right on the smell pattern. But just for a brief overview, this is a bit too busy, this plot, so please don't try to read it all. But just to give you a brief overview, that we sampled different areas throughout the core with different dust concentrations, but we always tried to get an area, to sample an area where we have quite a lot of dust, because finding those micro inclusions is quite a lot of work if there's not much dust in the ice, especially in the Holocene. Okay, this slide just shows the workflow again. So first you do the surface scan, you analyze the grain boundaries and map them. Then we go below the surface, map the inclusions in the sample, and then we go into details and do our Raman spectroscopy and try to measure as many of those inclusions as possible. And this is what you get in the end. You get a map of grain boundaries, of inclusions, and of identified minerals. So here you can see some gypsum inclusions, some quartz, some mica, some nitrate, hematite, feldspar, and so on. This is basically the workflow for our samples. Okay, I split this up into locations, so the distribution of those inclusions and the chemistry, and just some results. So what we found is that the inclusions, they are definitely not homogeneously distributed. You have areas where there are quite a lot of them. They build little clusters. You can see on the figure on the bottom left, those tiny circles, they show you clusters of inclusions, and also on the right, those elongated circles or ellipses, they show clusters of inclusions. And if you look at the overview scan above, you can see that some of them are very, somehow randomly distributed, and some of them are very solitarily located, so there are no inclusions around. So the spatial scale is definitely something to keep in mind. It really depends if you look at the broad scale or if you really go into detail. Okay, then we did some statistics. So we analyzed all the inclusions which are found at grain boundaries. So we did an upper limit assumption. Those grain boundaries here, they are too thick. In reality, they're just a couple of nanometers, and we estimated a width of 300 micrometers to account for the, since we're in the sample and the birefringence and all those effects, and therefore we set an upper limit of 300 micrometers and just counted all the inclusions which are located at those grain boundaries, which are between 22 and 41%, on average 30.9%. And then we did the same for the grain boundaries. How much area are grain boundaries accounting for in the sample? So this is a similar figure between 19.6 and 43%, on average 26%. And out of this, you can get a ratio if you divide the inclusions at grain boundaries by the area occupied by grain boundaries. So this gave us a little estimate how this is changing throughout the core and also inside the sample. And the basic result here is that the majority of inclusions is in the grain interior, but there are, in half of all the samples, there are more inclusions at the grain boundaries than you would expect from your grain boundary area. This is one of the big debates in impurity localization research in ice. Where are those inclusions? And grain boundaries are, of course, one of the main areas they are expected to be. Okay, so this is it for the localization part, and now a bit more into the chemistry. I'm not a chemist myself, so yeah, I'll try to do it correctly. But you mainly find insoluble mineral dust like quartz, feldspar, mica. These are the main minerals we have in dust storms, or which came from Asia or from the Gobi Desert to Greenland. And then we have a lot of other minerals, like especially sulfates, which are then again, which gypsum is one of the main sulfates which we find in general, and some other minerals which are there in very low abundance, like hematite or rutile. Okay, this is the overview of the entire core we've done so far and of each depth. And you can see here that there are some minerals we always find, like quartz, like gypsum, mostly feldspar and mica, and then a lot of different sulfates in the upper 900 meters. So the dotted red line you can see here is the boundary between the sulfate diverse area of the core and the gypsum dominated area of the core of our samples. So at 900 meters, we have the switch, and you can see it in the, in this reddish brown color, the bottom bar, which really decreases after 900 meters, so on the right. And here again in detail, these are only sulfates now. And on the left, above 900 meters, you can see there's a variety of sulfates. So magnesium sulfates, nitrate sulfates, gypsum, of course, some undefined sulfates. And below 900 meters, we only find gypsum, except one little inclusion, which was not gypsum, but another one, chronkite. So this is really something new. We weren't aware of this before. And yeah, gypsum only here. And now, of course, there's the question, what is or was going on below 900 meters, or to put it into your time frame, 7.6 thousand years ago. This is one of the main questions we try to answer in our papers. And now, putting both things together, so the chemistry, so the minerals and the localization of those inclusions, we came up with those maps and tried to find spatial patterns. And on the upper left, you can always see the depth. And down below, you can see the legend of those inclusions, which we could identify. And you can see that there are often layers. Especially in this is the very shallow sample. And in these layers, you can have clusters. And these clusters are normally sulfates. And this goes on for the entire core. So blue is also a sulfate. Blue is a gypsum. but I colored them in blue because they are so rich and abundant. So don't confuse, but all those orange dots, they are different kinds of sulfates. Yeah, and here you can see some examples of clustered sulfates. And the same is true for different depths. So here again, we have this layer of magnesium sulfate mainly. A little bit above, there are different sulfates, and then gypsum, really creating those layers or those clusters, and also at 900 meters. And if you look at the sample below from 1062 meters, you can see that there are no orange dots anymore, so no other sulfates than gypsum, and the clustering is also much less. So this is quite an interesting thing, and we are still trying to really get behind it. Maybe some of you have some really good ideas what could be the reasons for that. And to summarize this, I came up with this little figure. So we classified the upper 900 meters of the EGRIP ice core, that you have large grains, you have sulfate layers and clusters, you have gypsum throughout the sample. Mineral dust is also very dominant. Sometimes we have layers of mica, which are not really distinct layers, but more broader areas. And the lower part, I call it the lower Holocene, you have, of course, smaller grains due to getting closer to the glacial, where you have the small grain size. You only have gypsum nitrate start to appear. We still have those mica layers. Hematite is more abundant. And yeah, sometimes you also have ametars. Okay. So what I think is still to consider, of course, there are a lot of effects which we can't really grasp in detail. So of course, minerals, when they are getting, or dust and inclusions, when they are getting transported to the ice sheet, there are things happening. So during the transport, when they are in the snow, we know that chemical processes already take place in snow. So this is probably the same for ice. And there are also some other people working on chemical reactions going on in ice. So this is quite a hot topic at the moment. We have large scale changes. So at those 7.6 thousand years ago, there were some changes from the Greenland ice sheet. So the ice sheet retreated, came back, retreated. Sea ice cover was different. So this could have an impact on your mineralogy, where your dust is coming from. And of course, we are on an ice stream. So the deposited dust particles, they weren't deposited at the place where EGRIP is being drilled right now, but somewhere upstream. And on the right plot, you can see the age scale and the estimated upstream correction where the ice was coming from. So this is some, I think, 200, 300 kilometers away from the EGRIP drilling site. It's the glacial. So this is also something which is being worked on since it's such a young core. We don't have all this data yet, but these are things to keep in mind. All right, and also this plot clearly shows that impurities, they definitely go hand in hand with your deformation and your microstructure, especially in an ice stream. And this brings me to my last slide. So the work here in Venice, because we try to get together and to combine our Raman data with the laser ablation data Pascal has been doing here in Venice for some time now. I think you're all aware of the method. So we ablate the upper surface of the sample and measure the elements in there, and we can also image them. And for the last 1.5 months, we have been analyzing the samples, the same samples I've been doing Raman spectroscopy on. We shipped them down here, and we did a lot of laser ablation measurements on them, despite a lot of difficulties. But we were quite successful already. So here's one example with 35 micrometer laser spot size of sodium at 1,140 meters of depth. And just to show you some new, very preliminary data, we increased the resolution. So we went down to 20 micrometer laser spot size. Here at a different sample, the oldest one, almost the oldest one I brought down to Venice. And there are some really interesting patterns which we are trying to get behind now, trying to combine this microstructure and this impurity approach. And therefore, it is especially interesting to go towards a very high resolution, to have this really small laser spot size, 10 micrometers, the lowest we could go so far, because then, and also at some other samples with higher laser spot sizes, we can really see those inclusions. So especially on the right for aluminium, you can see a lot of dots, and these are several pixels, which are very likely to be similar to the inclusions we have seen, or clusters of inclusions. So the goal is to do some statistics on them, to do chemical comparisons. Does the element chemistry fit the mineral chemistry we find in those samples? And there's a lot of work ahead, but I think we did a really good measuring campaign here. And there are some preliminary conclusions, such as that the basic properties, so where do we have a lot of impurities? Do we see layers? They are similar in Raman data and in laser ablation data. So the comparison between those both methods is quite successful. We definitely see elements like sodium, which are located at grain boundaries mostly, but there are definitely other elements like aluminium or iron, which are more in the grain interior or building those micro inclusions. And therefore, again, the small scale variability can be quite high. So this is something that always has to be kept in mind. Yeah, that's it for now. Thanks for your attention. Mille grazie. And yeah, let me know if you have any questions, or also feel free to write me a mail later. I'll be here for another 1.5 weeks if you have something really urgent. Thank you.